Why are we here today? Well, Anton and I actually contacted each other 6 months ago, and we said, hey, you need to read this book. I really recommend this book. And we both said, hey, it's the book of why. So, and we also said that we're looking into this YouTube video about Julia Pearl, and that was the same day. And so we said, hey, we should really get on top of this topic, and we got into this subject, and that's how we got here and to this event. But why should you really listen to us doing this introduction? So I work with airline operators and handle their airline safety, especially in the recent events of the 747 MAX. We've had a lot of incentives to do correlation and causation analysis for most of our customers. So it got really handy with this kind of framework. And Anton, he is a machine learning engineer at Sona Labs, where they're recommending content for students at the optimum, really the optimum content, causing a better learning path for them on online platforms. It's really amazing work. So shout out to Anton and the Sona Lab guys here. And
yeah.
this, yes, this is working. Yes.
I'm working.
So this topic really, and one of the professors here, this is hard to deduce. This is what it's all about.
Yeah, so it's really nice to be here talk about this fascinating concept. I guess more than one person has seen this comic before. Otherwise, it's really. So the idea is that the guy is confused about if there was a causal effect by taking a class and learning something. And I know that there's tons of really smart people that think that you can't infer causal effects only from observational data. But this is wrong, actually. And it's just in the last few decades. Does it work? It does work. I just have to learn this. It's just like in the last few decades that there has been something which people refer to as a causal revolution, where you have been able to formalize when does correlation actually imply causation. So that's why we can stand here and have this causal summit, because of changes in this field, in fact. But before we talk about how do you infer causality from correlation, you have to make sure that you're actually observing a correlation. So, Eric, would you say that there are different types of correlations?
Yes, we have the real correlations, right, that we find in nature. But we also have a thing called spurious correlation, which really is complete random correlations that happen if you measure a bunch of things. And we'll show that to you. So the here is one classic example. There's a multitude of these, where you have autism rising together with organic food cells. So is the amount of autism inferring that there's more organic food cells, or is it the opposite, that if you eat organic food, maybe you develop autism? It's highly correlated. So what they've done is just to narrow down the population and really measure the right stuff to make this possible. And this correlation is quite high. There is a site with all of these spurious correlations that you can find. And the more US spends on science, the more hangings. Very interesting. Or is it the opposite? Maybe more hangings leads to spending. Could you scroll down? There's one favorite here. Just scroll down a bit more. So, no, you just missed it. I want the margarine thing. So if you want to keep your relationship with or have your marriage intact, stop eating butter. Just stop eating butter. That's what this says. And we will provide a link to this. This is just looking at enormous amounts of variables out there and just really picking the variables. And in the end, if you measure a bunch of variables together, chances become quite high that you will actually find a correlation. Because you are measuring these things, you can measure the plant growth of the anatomized plant here together with something else, and you'll probably find a correlation.
So basically, you're saying that there are spurious correlations, which you just observe and are not actually caused by anything, and then there's things that are actually real correlations between variables.
Yes, they're either due to utter coincidence or correlated by some unknown factor, really. So we'll come to that. So when given that you have this real correlation, so it's statistically significant, and you have this correlation. We deal with this every day, probably, or most of you people here. We have the data, so from X we can actually predict Y, or vice versa, we can predict X using Y. It's very common, everyone knows this, and this is what's happening today with deep learning. However, on the opposite side, you actually have a direction, and this direction can be either way, but changing values in Y, in the right case, will not change the variables within X. Do you agree on this? Yes. So, changing values in X happens so that it changes Y, in this case. So, the difference is really, on the left side you can predict stuff with both of them. But on the right side, you can infer sort of what is actually causing a change within the variables.
Right, so we have a definition of causality here.
Yeah.
And just in general, we said that you can have spurious correlations, and then you can have these real correlations. And if you have a real correlation, does this mean that there is some causal effect going on? What do you think? Yes, raise your hand. Wow, one hand, great. So actually, it turns out...
Can I ask again? Given that you have real connection between two variables, do you think there is a causal mechanism always?
What's a real connection or real correlation?
So it's something that as you gather more data, as you have infinite amounts of data, you will still see the same pattern. That is what a real relationship is. Statistically. No? So good question. It turns out that there is always... So it turns out there is always some causal effect if you observe a real correlation or a statistical relationship, but it doesn't have to be between those variables. These are the only three causal alternatives that exist, and in many cases there is some hidden third variable that you do not observe that is causing both of the variables that you do observe and that you're interested in looking at the causation between them. So the only thing we have to investigate is if there is any of the cases on the right side here are true. So this is called Leijonmarck's principle. I think I have a problem here.
Interesting.
So out of curiosity, the answer to your question, was it yes or no?
It was yes.
Yes!
So it's one of these three possible solutions to the correlation. So we actually have a clear example, and we're going to solve this tonight, or how you would approach the problem. It's a classical debate of smoking causing lung cancer. In the 1950s, the British Medical Journal posted this article on smoking causes lung cancer. And it's a very good study, and it's statistically significant. However, very intelligent mathematical people in our century, right? They're very famous, backed by the tobacco industry, gave a statement to the government because the government wanted to introduce a tobacco tax, and so what they cleverly did was say, by mere association with smoking and lung cancer, you cannot deduce the causal effect. So they were really clever and said this to the government, and the government didn't entail a tax on smoking. So we found a very small clip on this here.
So far, what are the conclusions reached by the organisation?
That there is need for much more research over a wide area, and in my opinion, to single out smoking as a causal agent is, on the evidence to date, completely unjustified.
Well, thank you very much, sir, for your help.
Well, thank you very much for letting me put our views forward. You better have a cigarette before you go.
Right. So unfortunately, a lot of people died because of this. But like it took a long time until you actually said that smoking does cause cancer. But the smart mathematicians, they were kind of right. You can't know unless we have these new tools that we have more of today. And like this is a pretty difficult topic, but we're trying to simplify it now. We're going to give you three really powerful techniques that can help you infer causes from observational data. So the example is, does smoking cause cancer? And as we saw before, there are three different options here. Either smoking does cause cancer. So let's say we observe some relationship, some correlation between these two. Either smoking does cause cancer, or cancer causes smoking, I don't know. Or there is something else that is causing both of them. Like someone's personal background or having unhealthy lifestyle in general causes both of them. And if we wouldn't be able to disregard this alternative that cancer causes smoking, this would be much more difficult. I guess you wouldn't be able to say anything about the exact directions, but if we know that we measure smoking first and cancer afterwards, we can rule this out, and then we only have the two other ones. So the most general case is that all of these directions are true, and what we can do with data now is to see how large are these effects, how large are the arrows here, and are they non-zero? So potentially there are no effects. There is no effect on the question mark.
So how do we get to these conclusions about the arrows? Are we
the Leijonmarck's principle, right? There are just three options if we observe the correlation.
But I'm referring to the directions of these arrows. So are we saying something about that?
So we know that it could be this, or a compound, a hidden cause here. And we know that cancer doesn't cause smoking. We have to rule that out because of the time variation here between these observations.
So you're saying that we're actually saying that the arrow should be to the right. So we're not using data, we're just using domain knowledge.
And without any type of domain knowledge, you can't do much causal inference at all. So you need this assumption something. I'm going to stand here. And the first approach for inferring causality, you force people to smoke. Then it becomes really simple. Then we only have to look at smoking and the correlation between it with cancer, because you were deciding if someone smoked or not. And this is what we can't do here. The gold standard of randomly controlled trials. If we only have observational data, now it starts to become like what is called causal inference, which is interesting. If we can measure something else, we can measure the confounders, we can measure people's personal backgrounds in some way. Then we can use the most common technique in causal inference, and it's just called adjusting for all the confounders. So what you do here is that you look at how much of cancer can you predict with the personal background? Can you predict everything, like exactly, or most of it? And then you look, once you've predicted as much as you can with personal background, is there some additional evidence that you can find from smoking? Do you need to know if someone smokes to be able to predict more? And if that's true, there's a causal effect. So that's called the backdoor adjustment, or just adjusting for confounders. And I would say the most common approach. The second approach, again, the background is typically too difficult. You can't do this in general. But if you don't do this, but you know about how the effect works, how the mechanism of smoking causing cancer works. I'll just also, for people without equations, this is how you do it. You would fit the model for approach 2 still, and they would look at does the coefficient for smoking become non-zero.
So in this case, we're doing a basic linear regression, right?
Yeah, for example, so you fit the model and you see is there a positive effect. But in the second approach, you know something about the mechanism. So you know that there is some effect that you can measure the mediator in it. So this is the mediator. The tar in your lungs is what is causing cancer. If you can do this, and then you only have to look at the correlation between smoking and tar in your lung, and then you look at the correlation between tar in your lung and cancer, and you're done. But this relies on the assumption that tar in your lung is not affected by something else, like a hidden variable like your personal background. But if you have some data set that you want to try to apply this, you can think about, is there something like this? And if you have it, then you can do really powerful things. So there's some cool studies that compare this approach with the ordinary adjusting for confounders approach. And this is often more powerful if it works. There's finally the third approach, which is quite old and also works really well. If you can find something else to measure again, and that's a cause of the treatment, or a cause of smoking in this case. And in this case, you need this instrumental variable, which is the proximity to a tobacco store, for example. You need this to actually affect smoking, and not directly affect cancer. This might be true in this case. Like if you live close to a tobacco store, you might buy cigarettes more often. And there is no confounder that affects your proximity to a tobacco store. So before we had this too complicated relationship with personal background that you can't measure. But if you can measure your proximity to a tobacco store, then you can actually, like I'll show some equations here. You just, again, look at the relationships. You pick the model, for example. How does proximity to a tobacco store affect smoking? How does proximity to a tobacco store affect cancer? And then you can understand what is the actual effect between smoking and cancer. So those are the just 3 very powerful techniques that you can read more on. I would recommend. There's finally a 4th technique, right?
You have more generalized, which is in the book, and very math intensive. So we have actually skipped that.
So this is why there is a causal revolution actually, that you're able to formalize when you can do causal inference, and it's referred to as do calculus, and it's a way to derive why all of the other approaches work pretty much. And yeah, this is the kind of work you do when you work with that. And if you don't have a simple assumption as we have here, then you need to do calculus or something similar to know what kind of correlations you have to look at to derive the causal effects.
And this can be used for time sequential causal effects, right? As well.
Anything goes.
Anything
but you
goes.
have to put in a lot of hard work.
So we've come to our conclusion. Hopefully you've had ways of dealing with this very hard topic, correlation and causation. It's still like the XKCD thing where you say, well, maybe I've understood this concept, because it's a quite large investment. If you just run away from here right now, we just want to give you 3 things that you need to remember, okay?
You have to remember it.
Yes.
So what's that? You shouldn't mistake correlations or spurious correlations. That's where a lot of confusion about causality comes from. And there are real correlations, and you have to make sure you're not regarding too many hypotheses and then randomly finding them.
And be aware of the confounder as well, because that can be a hidden variable. So that's the next part.
Right. There is always a causation if you observe a real correlation. That's surprising to a lot of people. But there is often, I guess, in most cases, a hidden factor that doesn't make it a direct causal effect. Finally, we showed 3 cool techniques that you should remember that they exist and that you can use
to actually have a causal inference. But be aware, because you have to know what you're doing. You have to know how you make the assumptions of these errors to the different variables, because you will actually infer it's like placing a prior onto your model, but the prior is quite heavy on how the model will actually output your causal inference. So that's the introduction. Thank you. Thank you. Now we have some questions. We have about 1 minute. Yes?
When you approach the problem this way with painting the arrows and so on, do you exclude that the causation can go both ways?
I think what you want to do with causation goes 2 ways. You introduce more variables so that you say that x causes y and y causes x.
Yeah.
But what you actually have is that you have a time series of x and time series of y, and that they cause each other, but only in the future direction. Does this make sense? So you should define more variables, and then it's possible. Otherwise, it's messy.
And as Anton said, you have to walk through it sequentially, if you have the sequential data. Yeah?
Great, just one question.
Any question? It's So if I repeat the question,
what's your threshold to say it's a spurious correlations? If you say if you have many variables, you can just apply chance.
Great question. So, what's the threshold for saying that you have a real correlation? And this is old school statistics. This is not with causal inference. And what you do is that you look at the significance level, the p-value, and you adjust for the number of hypotheses that you try out. So if you have millions of hypotheses, you have to adjust for that you have a million of hypotheses.
And if you measure a lot of variables and have a small data set, then that will probably cause spurious correlations. So be aware of that.